How's that go? Any questions on anything that you've reviewed so far? Because basically everything we've done thus far has been algebra. You guys had that as a freshman, right? That was 2 years ago. That's why this is so easy. Right? You agree with me? It's been pretty straightforward. No, it's not 10 times worse. It just gets a little bit worse every day. No, but today we are going to get into a concept which is not, it's mathematical, but it's not necessarily from math, and that's the idea of accuracy and precision. We're picking up on page 21 in the text if you're following along. If you're reading in advance at night, you've already read this, and so there's no surprise on what we're doing. If you haven't read it, we are discussing the difference between accuracy and precision, and I've already alluded to this a few times already in the class on the difference between accuracy and precision. Without reading from your book, does anyone want to give a shot on the difference between accuracy and precision? Because frankly, we tend to use the two terms interchangeably, but they mean something specific in science and specifically in chemistry. They mean different things. They're not exactly the same concept. Go ahead.
Precision is like the exact measurement, like.
Okay.
And accuracy is not exactly. It's exactly
Okay, so you're kind of dancing with the idea of exactness, right? Let's change that from exactness to correctness. Okay? Let's think about accuracy and precision in terms of correctness. Now, if I have two measurements, if I measured the length of a stick, and I had two different results, let's say that I asked Ray, I asked you to go ahead and measure a stick, and you went ahead and you went to the drawers and you found some measuring device and you measured it and you came back and you told me that that stick was 3 inches long. Okay? And I went ahead and sent Tyler out to do a measurement as well. He found another measuring device, measured that same stick, and came back and told me, Mr. Baker, that stick is 3.175 inches long. Can you tell me which of those two is more accurate? Which is more, yeah, just leave it at that. Which is more accurate? No, what the precision and accuracy, those are two different terms, right? Which is more, let's talk about accurate and contrast that with precise or precision. Which is more accurate or which is more precise? And if I ask you which of these is more accurate, can you tell me?
3 inches. 3.15 inches.
No. Neither. I can't tell. I can't tell how accurate you are. I mean, what if the stick is actually 7 inches long? What if you guys both messed up terribly on your measurements? The stick is actually 7 inches long. Who's more accurate? I wouldn't know until I knew what should they have received. What should they have measured it as? If I come back and say, you know what? Interesting thing, the stick is actually 3.02 inches long. Who is more accurate? 3 inches, right? They are closer to giving me a measurement which represents what that stick length actually is. If I say measure it, I come back with these two measurements. Who's more accurate? You don't know. I say, well, they should have given me a measurement of 3.02 inches. Now who's more accurate? Well, 3 inches is closer to the right answer than 3.175 is, right? This measurement is closer to being true, correct, and therefore it's more accurate. Now the other side is this idea of precision. If I did not know how long the stick was, and I asked the question, which of these two measurements is more precise? Can I come up with an answer? Without knowing how long the stick actually is? Yes, I can. I can tell you which of these two measurements is more precise, but I can't tell you which one is more accurate. Which one of these would you suggest is more precise? 3 inches or 3.175 inches? 3.175 is more precise, right? It measures to a much finer degree, right? Remember we talked about reading measurements, like using the metric, using the ruler or using the graduated cylinder, and I said you can always take your device, read it to the highest level of precision it indicates, like if it gives you milliliters, and then each milliliter is divided by 10 segments, I can go 2.5, I can read that, but I can always estimate to one more level. And I said you can always estimate to one more level of precision, right? One more level of precision. If my device goes to the tenths place, we've got, I'm just going to count up from 1 to 9. 1.2, 3, 4, 5, 6, 7. Hopefully remember that this is the units place. Then we have the tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths place, right? If I have a number, in this case 3.175, this is the tenths, hundredths, thousandths. What do I know about the instrument that Tyler used to get this measurement? How accurate, or excuse me, how precise, see, I sometimes use the words interchangeably too. It's not accurate. It's not accurate to use precision when you're talking about accuracy, and it's not precise to use accuracy when you're talking about precision. If I have a measurement of 3.175, what do I know about the device he used to come up with that measurement? How far can it read? He gave me an answer to the thousandths, but I'm always going to assume that he estimated the last one. He couldn't read it. He estimated it. So his device could read out to the hundredths place, okay? Which meant, in this case, if it's a ruler, he actually had a ruler that had 100 tick marks between 1 inch and 2 inch, between 2 inches and 3 inches, 99 tick marks to represent 100 places. So he could look at that ruler and say, I lined it up with the 1, it's somewhere past the 4, which means I start with a 3, and it's at the 17 hundredths tick mark. But it's a little bit longer than the 17 hundredths tick mark. Matter of fact, it's between the 17th and the 18th tick mark. Matter of fact, to me, it looks like it's exactly halfway between the 17th and the 18th tick mark. I'm going to give it a value of 5 in the thousandths place. I'm going to estimate it one more level of precision than what my instrument can read. But here's the deal. Let's say, I know this would never happen, Tyler, but let's say that inadvertently he forgot that he started at the 1 rather than at the 0. And so when he measured it, he saw the end of the stick, he read down and he said, I'm reading it at just past the 4, but he forgot to remove the 1, right? It should have been 3, but he says 4 and reads it as 4.175. While his answer is still very precise, it's very inaccurate. It's a whole inch off. I mean, it's like 25% off, right? He should have had 3, but he had 4. Major error. However, it's still very precise because he's able to estimate out the thousandths place. In this case here, what does this say about Ray's ruler, the ruler that Ray used? If he came back with an answer, Mr. Baker, it's 3 inches long. Well, he had a ruler that had no inch marks. He just had beginning, end. Looks like it's about 30% of the way. I'm going to give it a 3 inch. See? So what this tells me when I look at numbers like this, I don't know when I just see raw numbers, I don't know how accurate they are. Unless I'm told what it should be, I don't know how accurate. But I can tell how precise. And by knowing how precise, I can say what kind of instrument you use to come up with that number. If I look down and say, or I ask you to say, go out and, Serena, go out and make another measurement. Find something else, some other tool that'll measure that same stick. And she comes back and says, well, I've got this micrometer or this other laser distance finder or something like that, and she comes back and says, you know what? It's actually 3.1, excuse me, I wrote a 7, but meant 1, 3.1732598 inches long. I look at that, I can think a couple things. I can think, well, okay, she used the same ruler that Ray used, and she's just making this up. She's just winging it, throwing something out there. Or, if she actually understands what she's doing scientifically, she found an instrument that could read all the way out to this place here. Tenths, hundreds, thousands, 10,000s, 100,000s, millions. She found a tool that can measure out to the millions place, and she estimated out to the 10 millionths place. There's value in knowing that. Because I know if she's accurate, then I have a measurement which is very precise. Now, which do you think is more expensive to create? A ruler that has no inch marks on it, or a device that can read out to the millionths place in inches? Which would you rather make for money if you could do it, right? You'd like to sell these things all day long. Because people that care about taking it out to the millions mark, that they're concerned about that level of precision, it's difficult to make, and they're willing to pay good money to have devices that are that precise. This ruler here with no inches, some guy in his garage is taking pieces of balsa wood and just cutting them off with a table saw and giving them to you. There's no real concern. This right here is not going to be very precise. But if I happen to have a stick which is exactly 1 foot long, and I have this measurement, this device here actually has a exactly 1 foot measurement on it, this could do the job. I may not have to pay hundreds of thousands or maybe millions of dollars to get this tool, when I can go pay a quarter to get this tool. So what you need to take away from this is that accuracy and precision, first of all, accuracy, you can't tell if something is accurate until you figure out what it should be. And we may never know exactly what it should be, right? Unless it becomes the standard. I mentioned before, what's the length of a foot? Used to be the length of the king's foot. Now, in the Smithsonian Institution, they have a bar, which is the length of a foot. And every foot that we use in the nation is based upon that foot. How long is that foot? By definition, it's a foot. How do you know? Because it is the definition of a foot. If it were different, the foot would be different. It's kind of like this. Can God sin? We'd say, no, he can't sin. But if God did something we thought was sin, it wouldn't be sin. Because sin is defined as something that's contrary to the nature of God. So if God did it, it wouldn't be sin, so God cannot sin, right? Because everything is sin relative to who he is. Same thing with a foot. If it's a foot, it's only a foot if it perfectly matches the length of the standard foot, which is kept in the Smithsonian Institution. If it's not exactly the same length as that foot, it's not a true foot. It's something a little bit more or less than a foot. So how do we measure it? Well, different tools give us different precision. So the tools give us the precision. The accuracy is how we use the tools. If Serena did the same thing that Tyler did, and she had this tool that measured all the way out to the 10 millionths place, okay, or the millionths place, but she, for whatever reason, that tool had a benchmark that she chose other than 0, and she forgot to remove the inch. Now she gives me an answer that says, Mr. Baker, that stick is 4.1732598 inches long. Who's the most precise? She is the most precise by a long run. Who's the most accurate? It's still Ray with his stick 1 foot long with no inch marks on it. He's the most accurate. She's the most precise. Starting to see the difference? In the book, the way they communicate this is they show these three different bullseyes on page 22, figure 1-3. They're comparing precision with accuracy. And the first bullseye they show, this person throwing the darts, I'm used to using rounds, like on a shooting range. So this first pattern all the way on the left here, all those darts are in a very tight pattern. And a tight pattern in shooting shows precision. They're very tight. They're very together. What that means is the person making that shot is doing the same basic thing over and over and over and over again. And they can pretty much figure out where the next round's going to go because they're clustered in a very tight pattern. You see it here on this bullseye up at about the 1 o'clock position. It's a very tight pattern that shows precision. But guess what? They're not near the bullseye. Okay? They're not close to being accurate. They're precise because they're all very much the same, but they're not near the bullseye. The second case here, you can see accuracy. They've got at least one dart they're showing directly in the bullseye and a cluster that's around the bullseye. It's not all in the bullseye, but you see how the pattern is much broader than the first pattern. It's a broader pattern, but it's more centered than the other one, which means that the second person throwing darts here is much more accurate, much more getting the right answer, but yet they've got a lot of variation, so they don't have a tight pattern. Sometimes if we make the analogy of making measurements, sometimes they're measuring it and they're measuring it way long, and sometimes they're measuring it and they're getting it really short. But they're bouncing around the right answer. But their technique is off in the way they use their tool, and they're not consistently getting, they don't have a pattern to get the same answer repeatedly. And the third example shows both accuracy and precision. In the third bullseye, the person throwing the darts is both precise, because they have a very small pattern, they keep getting approximately the same answer, and they're also near the bullseye, meaning not only are they tight in getting the same answer, but the same answer they're getting is close to being the right answer every time. And so the trick here is getting the best tool you can get, which will give you the best precision, and then also having the best practices on how to use that tool so that you'll get the right answer more often. Now, there's always going to be error. Part of the human condition. We're always going to introduce error into the system. And so, if you consider on page 21, I'm just reading this. This is in blue, your definitions. Accuracy is an indication of how close to the measurement, how close a measurement is to the true value, whereas precision is the scale that the device uses. So precision is the tool, accuracy is you. You can have a very precise tool and completely waste its value because you use it wrong. You're not using the right tool for the job. It may be a very, very expensive tool. You go out and you buy a diamond-encrusted shovel to dig a hole for a pole, right? You're not using the right tool, you're using a very, very expensive tool that's not necessary for that. Other times you need something very, very precise, like a laser, but if you try to do it by eye, go, nah, that looks about right. You're not using the right tool for the job. And if you have the right tool and you don't use it well, why bother? You might as well have something cheap if you're going to use it wrong. They list in here several different ways that you can improve things. Like for accuracy, as I already said, it depends upon you. Precision depends upon the instrument. The only way to get something more precise, the only way you can get more precise is to invest in a better tool. Okay? Spend the money to get something that reads even more precision, more levels of precision. But there are several ways that you can improve your accuracy, and they mention those. First of all, when you measure something, don't just measure it one time. Measure it 3, 4, 5, 6, 7 times. And then after you've measured it all those times, look and see if any of those measurements are like way out there. Like, wait a minute, it should have been 3.17-ish inches. I've got 3.17, 1.38, 1.35, 1.39, and a 2. Well, guess what? I'm going to look at the 2 and throw that out. I'm not going to consider that. I'm going to take all the ones that are close, add them together, divide by the number, and get the average. The assumption is that your average answer is more accurate than any one of your individual answers. Another way then is to go and rather than just using the average of the measurements you make, is to take measurements from other people and average those together as well. So if you're on a lab team and there's 3 or 4 of you that have to figure out how long something is, well, each one of you could measure it once, then average those 4 together. Or, even better, each one of you measure it 4 times. Add all those, if there's 4 of you, there'll be 16 measurements. Add them all together and divide by 16 to get the average measurement from the whole group. Because again, you're not going to know what the actual measurement should be. You are going to be able to tell us what the measurement is that you were able to determine. And so you might come back and say, well, that stick is 3.175. Another group comes back and says, oh no, we averaged out to be 3.162. Which one is correct? Don't know. One of them might be closer to being correct, but we could do all the best, practices we can do in this room, and at the end of the day, average everything together and still not technically get an accurate number. But we are assuming by using those practices that it's going to be much closer to being accurate. All right? So again, if there's still some question about that, the idea is that precision is based upon the quality of the tool. Accuracy is based upon how you, as the user, use that tool, if you use it well or not. And I don't think you covered anything like that in algebra, right? So accuracy and precision. There is something we're going to do right now, though, that is going to be significant. That's my lead-in. It's going to be significant for what we do throughout this course. This is the idea of significant figures, Sig Figs. I'll say Sig Figs quite often in this course, and that just stands for significant figures. What is a significant figure? Well, this whole idea of accuracy and precision is tied into this idea of significant figures. And what we're going to do is show you ways to determine how many significant figures there actually are in a number and how far can I take it. In other words, if I have a tool that measures out 25 decimal places, I should be entitled to use that because I've invested in that tool. I should be entitled to use my measurement out to 26 places. However, if we're doing some mathematical operation on it, and let's say we're adding two pieces together, and one person has a tool that can measure it out to 25 places, and the other person has a tool that can only measure it out to 3 places, what would my answer look like, right? Can I use the same precision since I'm doing a mathematical operation on those two pieces? Well, that's what significant figures helps us figure out. So first we need to figure out what a sig fig is when we look at a number. Let's go ahead and use one of the examples that they use in the book. I'm going to use a longer one. All right. I'm going to be writing down example 1D, but we're going to use it as we apply the different rules of determining how many significant figures are in a number. I'm going to use 0.0045 0 0 1 0. All right. On the middle of page 23, the authors list 4 different steps that you're going to go through to determine how many significant figures are in this number. Okay? How many significant figures? The first one, I'm going to underline, as we look at each of these rules and apply it to this number here, I'm going to go ahead and underline the numbers that are determined to be significant. Okay, first of all non-zero digits are significant. So let's look at the number here. Where do we see non-zero digits? There's a 4, there's a 5, and there's a 1. So applying the first rule, all non-zero digits are significant. Second, all zeros in front of the first 1 through 9 are not significant. Okay? So look at the first significant figure you've come up with on the first. 4 is our first significant figure, right? It says that all zeros before that are not significant. So this is not significant, and not significant. Next, all zeros between significant figures are significant. So zeros before are not, but zeros between are. So where are there any additional significant figures in this number? Okay. So the zeros between the 5 and the 1. The 5 is significant, and the 1 is significant, and the zeros between them are significant, which are these two. And then the last rule is that all zeros at the end of the number and to the right of the decimal point are significant. Okay? So if it's a 0 at the end, and that 0 at the end is to the right of the decimal point, it is significant. So all zeros at the end, we have a 0 at the end, that are to the right of the decimal place, here's the decimal place, it's to the right, are significant. Okay? So the number here, 0.00450010, has how many sig figs? 1, 2, 3, 4, 5, 6. This has 6 sig figs, or significant figures. 6 significant figures. We'll talk about what we're going to do with them in a moment, but right now we just need to be able to determine how many any number has. So table 1.4 gives you some examples of significant figures. The first one, this shows 9,341. Are there any are there any zeros in that number? No. Every single digit is a 1 through 9 digit, right? Since every single digit is a 1 through 9 digit, every single digit is significant, so it has 4 significant figures. The second example looks a lot like this one, 0.000564. If we look at it real quickly, we have 3 non-zero digits at the end. Every other digit is before it and is a 0, and they're non-significant. So the second one only has 3 significant figures. Looking at the fourth example, 120.043. It has 2 non-zero digits in the front, 2 non-zero digits at the end, and zeros between them. Every 0 in there sits between significant figures, so every 0 in there is a significant figure. And that's why it shows that there are 6. And then lastly, zeros at the end of the number and to the right of the decimal point. Notice on the first one where it has 510.0. Let's look at this one on the board. 510.0, and the number is 510. Now, I started a couple days ago by saying we're going to learn that in chemistry, specifically, in science in general, that there's a difference between you giving me a measurement that says, hey, Mr. Baker, that was 510.0 milliliters, and Mr. Baker, that was 510 milliliters. You might think you're communicating exactly the same information, but you're not. I hear these two things differently when you say them. Let's look at the sig figs and we'll explain why. First of all, applying the rules. All non-zero digits are significant. So looking over here on the left, all non-zeros are significant. On the right, all non-zeros are significant. So far we've got 2 significant figures in each case. Second, all zeros in front of the first non-zero are insignificant. There are none, so this rule doesn't apply. Third, all zeros between 2 significant figures are significant. Are there any zeros between? No, there's no zeros between. Lastly, all zeros at the end of the number and to the right of the decimal place are significant. On this one, is there a 0 to the right of the decimal place? Okay, so this one would be significant, correct? Is there over here a 0 to the right of the decimal place? There's no decimal. So there's nothing to the right of the decimal place. Okay, now here's the trick that the book doesn't clarify, but you need to do. Now that I've gone through it one time, I'm going to go through it again. I'm going to apply the rules again, because if you stop right now after doing all 4 of these rules, you're going to miss one. Because by signifying that this last 0 is significant, suddenly we've altered this one in a way that we need to reconsider. Let's look over here. All 0 are All non-zeros are significant, we got it. All zeros in front are insignificant, we've got it. All zeros between significance. Oh, guess what? This one is now significant because we've determined this is significant. So now, that's a significant figure as well. See? And that will catch you if you just think of it as a one-step or a four-step process. Go through it, then I encourage you to go through it again. And after you go through it the second time, if you don't make any changes, then you're done. But if you make any changes, then do it again. Just keep running through the 4 steps until you make no changes, and then you're going to be finished. So in this case, there are 4 significant figures. Over here, there are only 2 significant figures. Okay? That's going to matter because in this case, I'm going to assume that you had a device that allowed you to measure out to the ones place, and you were able to estimate the tens place. Over here, or the tenths place, over here, I'm going to assume that you had a device that only measured to hundreds of milliliters, and you estimated to the tens place. See? This is a very imprecise tool. This is a very precise tool. Now, why does that really matter? It's because whenever we use significant figures, when we add them or we subtract them, when we multiply or we divide, how many significant figures that are present matters. I'm looking for where that is. I want to make sure we cover it and I don't skip over it. Okay. It's actually after scientific notation. So we're going to get to that shortly. But for right now, just having a number and determining how many significant figures that number has. Let's go ahead and try, if you haven't already, which again I hope you have, let's go ahead and try on your own 112 number, let's do B, 112B. Now, 112B is asking you to find the number of significant figures in 0.0060 meters. How many significant figures are in that measurement? I'm trying to figure out if a lip pencil's against dress code or not. 0.0060. Should we start calling on people in here? Would that be helpful? All right, let's walk through the process. All non-zero digits are significant. So, are there any non-zero digits? Okay. Okay, I appreciate bobbleheads, by the way. So if I ask a yes/no question, this is standard notation for yes, and this is standard notation for no. So when I sometimes say bobble with me, are there any non-zeros? Yes. So just a little notion. Feel free to let your neck loose. Loosen up a bit. Are there any non-zeros? Yes, there are some. And it's the number 6, right? This digit right here is significant because it is a non-zero digit. Second, all zeros in front of the first are non-significant. The first non-zero digit are insignificant. So those 3 are not significant. Third, all zeros between two significant figures are significant. Does that apply anywhere? Doesn't apply. Fourth, all zeros at the end and to the right of the decimal place are significant. At the end, yes. Is it to the right? Yes. Is it significant? Yes. Now, real quickly, looking back, are there any, we can apply it one more time just for consistency. All non-zeros, got it. All zeros in front are not, got it. All zeros between two, doesn't apply. All zeros at the end and to the right, yes. So there are two significant figures in that number. Tell you what I'd like to do is I'm kind of want to move forward a little bit. Now, if you actually did the reading, I think we're to the end of the reading, right? For those of you that did the reading. How many people think we've covered all the material that you were supposed to read last night? Hey, I know what we can do. Let's look real quickly to the back of the module, to page 41. Page 41 is the study guide for Module 1. Page 43 are the practice problems. And then back in the book, back in the appendices, just so you know where to find them, are the extra practice problems for Module 1. You can find those in Appendix B back on page 615. So for the homework for next week, you have homework from 41, 43, and page 615. Okay? Now, you might have been thinking so far, hey, I haven't had any chemistry homework this week, right? Hey, I haven't had turned in anything this week, right? Life in here, I just go and sit and listen. I have nothing to do, right? And what did I encourage you to do? To work through this homework during this week. Because if you save it to the last minute, next week, you're going to be going, there's so much chemistry to do. I can't get this done in one night. Well, you're not supposed to get it done in one night. You're supposed to be doing it this week so that you're ready, doing as much as you can. Because let's look real quickly at the study guide. Review question number 1. Which of the following contains no matter? We're not going to review that stuff again until it's due. We've already covered it. You've already read it. You can answer it, hopefully. List the basic metric units of length, mass, time, and volume. You can do that. In the metric system, what does the prefix milli mean? You can do that. All conversion factors when in the form of a fraction must equal. You can do that. Which has more liquid? Those two different measurements. You can do that. How long is the bar in the picture below? You can do that. Two students measure the mass in grams. The first measures 49.8123. The second measures, okay, which is precise, which is accurate. You can do that. Explain what a significant figure is. You can do that. How many significant figures are in the following numbers? You should be able to do that. A student measures the mass of an object in grams and measures the mass of another object in grams. She reports the combined mass. Is she correct? You can't do that one yet. You may be able to, but we haven't covered it yet. So questions 1 through 9 of your homework for Monday, we're not going to cover any more information than what you've already received from me. You might understand it better, but if you already understand it, you can answer questions 1 through 9 right now. So tonight you can start working on Monday's homework, which you've had since last week. Okay? If you look over to the practice problems, page 43. Convert from milliliters to liters. We're not going to cover any more information on how to do that than we've already done. Convert from kilometers to meters. Convert from kilograms to centigrams. Okay? If an object has a volume in milliliters, how many kiloliters does it occupy? 23 by 45 by 38. What's its volume? A nurse injects 31 cc's. How many liters? Convert the following into scientific notation. Okay, 1 through 6. We're not going to cover any more on that. You should be able to jump right in there and start doing problems 1 through 6. And I encourage you to do it. Whether it's tonight, tomorrow night, Friday night. But Friday night, you're going to say, well, that's my homework for Monday. Oh, look at how much it is. Start working on it now. We can't do 7 through 11 on the practice problems. For fun, let's flip back to the extra practice problems on page 615. Extra practice problems are given to you because these are problems that students typically continue to have trouble with. And so you should be able to look at these and say, wait a minute, the first one is measuring masses, which is precise and accurate. I can do that. How many centigrams are in a gram? I can do that. The volume, From milliliters to liters, you can do that. Inches to miles, you can do that. Kilometers to millimeters, you should be able to do that. Volume of a box, you should be able to do that. A string measurement of 32 inches, how many centimeters, you should be able to do that. How many hours are in 4,200 seconds? Again, you should be able to do that. Convert these to okay, up through number 9. Questions 1 through 8, we've already covered that content. You could complete questions 1 through 8 right now. Just module 1. This week, we're covering content module 1. Next week, we're doing homework and reviewing module 1. Next Friday is the module exam. Okay? So all we have left to do in this module really is scientific notation, multiplying and adding, dividing and subtracting significant figures, and converting between Celsius and Fahrenheit. And we have 3 days to do that, and then 5 days to review it, or 4 days to review it before the test. So again, this is just my encouragement to you to be into the homework the night before the night before it's due. You know, be looking ahead and answering what you can as you can. Now, the technique might be work those problems now, but you know what? It may click for you. We've already covered it, but it may click for you in a couple days. I understand that happens. So before you turn it in, go back and review what you've done. Say, hey, wait a minute, I did this work on Wednesday, but now it's Friday, and I'm much smarter on Friday than I was on Wednesday. So I'll review it and make sure that what I did on Wednesday is true. It's accurate. Okay? But again, if you wait until Sunday night, Monday night, or Tuesday night, or whatever the night before is, it's going to seem like a lot. Will I be sympathetic that it's a lot to do that night? Yeah, if you're stupid enough to wait till the night before. You come in, man, I was doing it for hours last night. Bad on you. When did you start? Last night? Okay, pay the piper. It's your choice. Or you can do 20 minutes a night until you're done, and then have it done before the weekend even comes. Because after Friday, we're not going to cover any new content. You're going to have it all. So next week's homework should all be accessible to you by the end of this week. And most of what you have for next week is already accessible to you. You've already covered it. Okay? So, put on the big boy pants and start doing your work in advance of the night before it's due. That's my encouragement to you. We're going to take just a moment and talk about scientific notation. There was able to fill enough time to get us ready so we can do scientific notation. Then tomorrow we'll move into application of significant figures and then converting between temperature scales. Just so you know, this is the first chapter. It's kind of like the intro into the culture of chemistry. We've had a couple extra days this module. Future modules will have more content in less days, and it will be a little less obvious. So we're kind of starting out with a jog, doing the first lap, maybe this part of the second lap, but then like a good runner, we're going to start kicking up the pace, and your final lap is going to be much faster than your first laps. We're still in the first lap. Again, not to discourage you, prepare you. If you're not reading now, when it's easy, you may not be ready. You may not have the discipline and practice to be reading when basically you have to read, because we're going to get into things that aren't intuitive. You're not going to be able to just look at it, hear me say it, and go, oh, I get it, it's easy. I mean, I'm not saying you're doing that now, but the constant encouragement in chemistry is you need to be in the book, you need to be paying attention in class, you need to be applying yourself, you need to, as much as possible, be working ahead, because there will be times when even the most disciplined person, even the person here that may get easy A's, is going to have something where they struggle. So be ready for that. And give yourself enough margin so that when you do struggle, you have the time to figure it out and catch up and then continue on. And I'm presuming that when I give these kind of pep talks, that I'm just being honest with you. You know, there's nothing hidden, no content that I'm going to like surprise you with at the last moment that, hey, it's 10 minutes left in class on Friday, but you need to know this for the exam. Boom. You're like, well, we never even heard that. It's all out there. It's all in the book. My tests are based upon the tests that this author creates based upon the content that he puts in the book. So if you're not reading the book, what I'm doing is highlighting things in the book. I'm teaching most of the content, but I might have missed something, not intentionally, okay? But it is part of the greater discussion. I'm not intentionally leaving anything out, but so everything that I present is coming from the book. The tests are based upon the author's tests, which he wrote, or they wrote. So I'm basing it off of that. So I'm not going to like pull some weird abstract thing and just decide to throw it on the exam and make you accountable for it. everything you need to know is in the book, and everything you need to know we're going to cover in class. So there's no secrets. You should know probably in the next day or so whether or not you get this or not, and if you need extra help, and what you need to do to catch up. Scientific notation. We've already done this a few different times, and it's basically just this idea of moving the decimal place. You can see a graphic on page 26 where he talks about the movement of decimal places. What I'd like to do is just cover the idea of negative exponents and what that means for mathematics. Like, for example, they show in blue on page 26, they show these long strings of numbers. 2 times 10 to the 22nd means it's a 2 with 22 zeros after it. If you want to write 2 with 22 zeros after it, that's fine, or you can use 2 times 10 to the 22nd. Down below that, you see 1.67 times 10 to the negative 27th. For a moment, let's think about different ways that we could write that number. 1.67 times 10 to the negative 27th. Okay. I'm going to start with something a little bit more basic. Let's just say I had the number 1 times 10 to the negative 27th. Again, you see the negative 27. What does that mean to you? That the decimal place is, like, it's implied to be right there after the 1, right? But if I were to write the number all the way out, it would actually be way over here with 26 zeros after the decimal place and 1 before the decimal place. It's a very, very, very small number. So the negative exponent shows me the degree of how small that number is, right? If this were to the 27th, that would be a very large number, right? It would be 1 point, then 27 zeros, 1 with 27 zeros following it, and then the decimal point. It would be a huge number. So a positive number means a large number of zeros to the right. A negative means a very small number with a large number of zeros to the left of whatever the coefficient is in front of it. Hopefully you can also see that 1 times 10 to the negative 27 could also be written as a fraction of 1 over 1 times 10 to the 27th. It's the same thing, okay? That a negative exponent on your scientific notation could be written as the same thing as a fraction over a positive 27. A negative and a positive. Do you remember that in scientific notation? When's the last time in math you worked with scientific notation? By the way, if you recall? I don't know, I'm asking. No clear answer. So is scientific notation something that you generally feel we get it, or is it generally something that's like, it's a weird concept you don't really understand? Okay. Lacking feedback and lacking time, then we'll go ahead and pick up with scientific notation tomorrow. Look at example 1.6 on page 27 in preparation. I mean, you've got reading through that period, through that session as well, or section as well, but please take a look at example 1.6. We'll talk about converting each of those numbers there into a scientific notation. Because there are going to be often there are going to be times when we're dealing with math where we have a scientific notation, both the numerator and the denominator. If we had something, for example, that was 3 times 10 to the 5th divided by 2 times 10 to the negative 3rd, we're going to need to know how to figure that out using scientific notation.